Hello, and welcome to episode 6 of CS350 Online. I'm your host, Leslie Eisted, as always. And on today's episode, we're going to cover semaphores and condition variables, which are the last things that you're going to need to get your assignment 1 fully implemented and submitted. So that's good news, right? Okay. Our operating system of the day then is an operating system called DTSS, not to be confused with Tuesday's operating system called CTSS. So DTSS was released in 1964 for the GE200 series of computers. And this particular operating system was out of Dartmouth College. And of course, DTSS stands for the Dartmouth time sharing system. Now, the name of the operating system should give you a pretty good indication as to what its main feature is, and that is time sharing. Now, what makes this particular operating system different from CTSS? Well, CTSS demonstrated that it was feasible to do time sharing, but DTSS is really the first large-scale operating system to offer time sharing. And what's interesting about it is when they created DTS, they had this kind of goal in mind. Instead of just creating an operating system that'll be used by just a few select individuals in the industry, why don't we write an operating system that could be used by everybody? And in fact, they went out with the goal of having as many people at the university as possible to use DTSS through their different programs. So by 1968, so in just 4 years, they say that 80% of the students at Dartmouth were actually using DTSS for something. Now that might give you the idea that, oh, it must be a tech school. But no, it's not necessarily a tech school. They were using this in arts programs, in history programs. They were integrating use of computers in with as many different courses and programs as possible, which is pretty cool for the time. Now, another interesting thing about DTSS is even though it was released in 1964, it actually remained in operation until 1999. That's a really, really long time to be in operation. Now, I'm sure it came down to it wasn't actually in wide use. I'm sure there was the odd professor that was still hanging on to it for dear life, as always happens. So what's interesting about this particular implementation of time sharing is they decided to abstract how the time sharing was implemented from the hardware. So they did use preemption, but they also wanted to make sure that the actual implementation of time sharing was abstracted from the hardware itself. So they had a pretty good design for it. When they were dealing with preemption, they wanted to make sure that any user sitting down at the computer would never have to wait more than 10 seconds for whatever request they have asked to be completed. Now, from a modern standpoint, 10 seconds is a really long period of time, but it's 1964, and 10 seconds is nothing, so they weren't too concerned about that. Some other things that DTSS provided us with was the first IDE, so you could actually have lines automatically typed and then inserted into the program, compiled, and executed. So you had that real interactive development environment provided with DTSS. All right then. So what happened last day? So last day we finished our discussion of spin locks and how we are using the architecturally provided atomic instructions to do an atomic test and set inside of our spin lock. Now, we use spin locks as kind of the wrapper for that atomic test and set operation in the architecture. And remember that spin locks, they are kind of the basic building block that we're going to use to build other tools with that are a little bit more user-friendly. It's not that spin locks aren't user-friendly, they're actually quite easy to use, but there are some issues with them. Number one, if you just implement a spin lock straight up, of course, you're going to have other threads actively spinning, wasting CPU's time while they try to acquire a spin lock which is already owned. So what we have done, and what many operating systems do, in order to reduce the amount of busy waiting that happens to other threads, is that they simply cause the spin lock to disable interrupts on that particular core while some thread owns that spin lock. Now, this has the positive side effect that on that particular core, preemption is halted. And so effectively, no other thread could realistically own or use that CPU. So we say instead of the spin lock being owned by a thread, we say the spin lock is owned by the CPU. Of course, this doesn't actually stop you from calling thread yield or anything like that, but that's on you to use the spin lock properly. So we don't have preemption happening on our core that is owned by the spin lock. So we're going to not have threads who are trying to run on the same core trying to acquire that same spin lock. So that's nice. However, it doesn't stop threads from trying to acquire that spin lock on other cores. So it is entirely possible that on other cores that we're going to end up doing some busy waiting, depending, of course, on the system's implementation. What this at the end of the day means is that spin locks are a necessary evil. They are nice for wrapping around the assembly language that we use for the atomic test and set operation, but we really shouldn't own a spin lock for a very long period of time, because if we do, what's going to end up happening is a lot of our interrupts are going to get ignored and possibly lost, and that would be bad. So instead, what we do with the spin lock is we're going to use a spin lock to help us implement other synchronization primitives, such as what we introduced last day, which is locks that block. And if you're looking to do assignment 1, part 1, implementing locks, please make sure you check out episode 5. Everything you need to know is there. All right. So what is this lock that you have to implement for assignment 1? Well, just to reiterate what it is, a spin lock spins and a lock blocks. So if a thread tries to acquire a lock and the lock is simply not available, then that thread is going to fall asleep on the lock's wait channel. What's nice about that is that that thread that's asleep on the thread's wait channel is not going to be in the ready pool, so it'll never be selected to run, and it's also not running on the CPU. And the only time which a thread that is being blocked can actually end up running is if some thread that does own the lock wakes up the thread that's on the wait channel. And when you wake up a thread that's on the wait channel, the thread doesn't go from blocked to running, it goes from blocked to ready. And then it has to do a little bit of additional wait while it waits for the operating system to schedule that particular thread to run. So it's also important to note that when you are woken up because someone has released the lock you were waiting on, there's still no guarantee that you are going to immediately run, which means it is possible for another thread to steal the lock out from under you. So if you're wondering why there's a while loop in the body of the lock acquire function, that's why. Because when you wake up, when you move from the blocked state to the ready state, it doesn't mean you're going to run immediately, which means other threads may run before you and they may call lock acquire and end up acquiring the lock instead. Now, as it turns out, if you do want the thread or the lock to be owned by threads in the order that they call acquire, a very teeny change to the implementation can give you that ability. But that's not necessary for your particular implementations. It used to be a common question we asked on midterms and finals, but that's not happening. All right. So let's move on then and talk about, since we're done with locks and we've shown you how locks are used and we've shown you some tests that you can run, let's actually move on to our next synchronization primitive, which is my personal favorite, the semaphore. So right now you have a synchronization primitive that can be used to guarantee mutual exclusion. So you have some critical section, you only want one thread in there at a time, and so you can use a lock as mutex to protect the critical section and make sure that you only have exactly one thread in there at any given time. Great. But there are other kinds of synchronization problems that can arise. What if I have some kind of critical section or some kind of block of code where I could technically allow more than one thread? That's an interesting idea. Because if I could technically allow, say, 5 threads, but no more, then I couldn't use a lock as easily. It's not to say you can't use a lock, you can. But how you would use it to do this is very different. So that's actually an interesting discussion then. Let's suppose you do have a block of code where you do want 5 or less threads to enter, but no more. How would you do that with a lock? Well, you know what? Instead of introducing the semaphore first, why don't we show you how you would do this behavior with a lock? So let's switch over here to a notebook. I've got the lines up by default today so I can write a little bit neater, although I'm not sure how well they actually show up. All right, so I want some kind of region of code where I can only have 5 or less threads. So I'm going to say, let's have some global variable called count. And it's going to start out at 0 because there are no threads in the critical section. And then we'll have some lock. And we'll assume that this is pseudocode and that the lock's been created and so on and so forth. So I'm just going to draw some dots here to indicate we did something. All right, now how do you let 5 but no more threads into the critical section? Well, first we need to check how many threads are in that section right now. And in order to check this shared variable count, we need to protect our access to it. So that's what we're going to use this lock for. So we are going to acquire our lock. There we go, that's not so bad. Now that we've acquired the lock, it's safe to check count. Now, if count is equal to 5, then what we're simply going to do is release the lock. Otherwise, we're going to wait. Now, instead of waiting here, I don't know why that showed up. There we go. Instead of waiting in some kind of explicit thing, what I'm just going to do is put release here. Actually, what we've implemented here doesn't work at all. Let's fix it up. We don't want to release the lock of count equals 5 because if we did, then we would be letting a thread into the section that we don't want threads in if the count is bigger than 5. So we're going to say instead, while count is greater than or equal to 5. We could use equals equals, it doesn't matter. We're just going to sit here and spin. How are we going to spin though? Because if I don't, here's the problem. If I don't release the lock, then nobody could change the count. So what we're going to need to do here is to give ownership to another thread in order to change the count variable. I'm going to have to actually release my lock. And then I'm actually going to call yield here because I want to encourage other threads to be able to finish their running and actually change the value of the counter. And then right after I yield, and this is still in the body of the loop here, I'm going to acquire the lock again so that when I loop around and I test the value of the lock again, I'm still protected. So there we go, that's nice. Now, if we leave the while loop, it means count is less than 5. So now what I want to do is increment the counter and then release the lock. And now I can go into my critical section down here. And so this was the enter part. And then to leave the critical section, we're going to, again, acquire the lock because we're going to need to modify count. And then we don't need to do any while loop. We're simply going to, since we're leaving, we're going to decrement the counter. And then we release the lock. There we go. And we do that when we leave. So this here is how you could use a lock in order to control specifically how many threads are permitted into a region of code. But this was a lot of work. A lot of work. And it would be really nice if we had a synchronization primitive that could do all of this junk for us, and we didn't have to worry about, did I use while, did I use the yield, did I use things in the right order, have I checked the right counter value? And that's what a semaphore gives us. So what we get with a semaphore is a semaphore, instead of letting only one thing into the critical section, a semaphore has a counter instead, and it's going to keep track of how many resources are available. So when we're talking about semaphores, we're usually talking about how many resources do we have available. So an example of how we would use a semaphore is, let's suppose that we were having an in-person lecture and our room seats 89 people. Well, that means there are 89 chairs in the room, so there are 89 resources. And when you go to enter the room, you're going to check, is there a free chair? If there's a free chair, that is, the number of resources is less than 89, the number of resources available is going to be something other than 0, then you would be like, okay, then I can enter the room and I can sit in a chair. But if you try to enter the classroom and the number of available resources is 0, then since you can't get a chair, you have to sit by the door and wait for someone to leave. So we can use a semaphore to keep account of how many resources are actually still available. Now, that means that internally, instead of having a Boolean to keep track of whether the item is owned or not, we're going to actually keep a counter. And the counter is going to count how many resources are available. Now, in our particular implementation of a semaphore, as you will see, you will note that our counter, when it reaches 0, means that there's no resources available, and we're not going to continue decrementing past 0 because there's no concept of you owe me a resource. That's silly for us. So how do you actually do the acquisition and release then of one of these resources with the semaphore? It would be very nice if we used acquire to acquire a resource and release to give a resource back, but we don't. Semaphores use these functions here, P and V. P, which is my understanding is for the Dutch word of passering, and I'm sorry, I do not speak the language, so I'm probably butchering the word. Its pronunciation is supposed to be meant to represent passing. And the V is for the Dutch word vrjgave. I'm not sure how to pronounce it. It's VRJIGAVE, which is supposed to mean release. And the reason why these functions are P and V for these two words is because the individual who created the semaphore in Dijkstra's paper, he was apparently quite fond of trains. And so he named his functions after train signals, or so the story goes. Of course, if you were a 135 or 136 student and you named your functions P and V, you would have lost all your style marks because those are horrible names for functions. I don't know what a P is. I don't know what a V is. And I'll be honest with you, it's pretty common for people using semaphores to mix the two up. So P is to get a resource and V is to release it. And when we're talking about semaphores, we're often referring to P'ing and V'ing the semaphore. And in OS 161, the semaphore is already implemented for you, so you don't need to worry about that. And the functions are P and V. But in some more modern libraries, you'll actually see that they've given P and V nice readable names. We don't have readable names. The other thing I want to point out is because P and V, they have been provided to you as atomic, that is, they already offer, there's no race conditions with them. All right. So what's interesting about semaphores, and probably the main reason why I like a semaphore so much, is the fact that you have this one beautifully simple tool that can be used in a variety of different ways. So with the single implementation of semaphores that you're going to see in a few minutes, we can use it in different ways to give us different kinds of control. So for example, a binary semaphore is a semaphore that starts with a single resource and it behaves just like a lock. So that's one of the things that you have to do when you create a semaphore, is you have to tell it how many resources does it have to start with. And that number can be 0 or more. What's interesting then is if you create a binary semaphore, you're going to create a semaphore with a singular resource. And then so long as you use it like a lock, where P is acquire and V is release, the semaphore behaves just like a lock. Now, does that mean you can implement a lock using a semaphore? Yes, but please don't do it on your assignment, as you'll lose all the marks for that. But there's one other interesting thing. Even though the binary semaphore can behave like a lock, it doesn't mean it is equivalent to a lock. For example, there's nothing stopping you with a semaphore from calling V multiple times. So I could have a semaphore that starts out with a single resource, and if I call V 3 times, my semaphore now has 4 resources. There's nothing wrong with that. If you think about it this way, let's suppose you own a bake shop, and when you wake up in the morning, the number of cupcakes you have on your display shelf is 0. So the number of resources you have available to sell is 0. So you have to go into the back room and you're going to bake some cupcakes, and then when they're done, you're going to put them on the shelf. So you are adding resources at a later date. You are V'ing your semaphore before anybody can actually try to acquire. And that's totally possible. So with a binary semaphore, we're not checking to make sure that we don't V multiple times in a row. So you, the user, has to be very careful about how you actually use it. The other thing about a binary semaphore is that it doesn't have a concept of ownership. So with a lock, we keep track of the owner because we don't want anyone who doesn't own the lock to try to unlock it, because they could let themselves into the critical section. Semaphores don't care about ownership, and anyone can release or call V on a semaphore, which means that if you're using a semaphore as a lock, you need to be very careful about ownership and is this okay. Think of it this way. The semaphore's kind of like, let's suppose somebody steals your laptop. Do you care more that your laptop is returned or who stole it? Now, I'm sure you'd like to know who stole it so you can get them in appropriate trouble, but you probably care more that your laptop's returned. So semaphores are kind of like that. They don't care who returns or produced the resource. They just keep track of how many there are. So we have binary semaphores. Now, we will come back to discussing binary semaphores and why they are important when we talk about devices closer to the end of the term. Now, what about the counting semaphore? Now, a counting semaphore is just a semaphore that has an arbitrary number of resources. So anything from 0 and up. And this is one where we may be calling V multiple times before P is ever counted. Now, what is a barrier semaphore? So again, these 3 semaphores are all using the exact same implementation, but the big difference here is how we're using them. So a barrier semaphore, remember how a while back I said we don't have thread join, which is we don't have the ability for one thread to wait for another thread to complete? Well, I said we didn't have join, but we still have the ability to do that. And the way that we can do that is by using a semaphore. So by using a semaphore, we can actually force a calling thread to wait for some other thread to complete before we move on. And if you look all through the thread test code and the traffic simulator code for assignment 1, you will notice that barrier semaphores are used pretty much everywhere to make sure that the threads that are doing some kind of computation complete their computation before it moves on to presenting the statistics or analysis of the computation. All right. So Just to give you a couple examples of using a semaphore, here's how you would do mutual exclusion with a semaphore. So we create a semaphore. We set its initial value to 1, so it has 1 resource. And then we simply make sure that before the critical section where we would normally call acquire, now we're going to P the semaphore, and where we would normally call release on the lock, we'll just V the semaphore. So here is that little snippet of code from the beginning of this module, and now we've just changed it to use a binary semaphore instead. Very, very simple. Now, what's interesting is now that we have semaphores, we have the ability to solve some interesting problems more simply. It's not that you can't solve them with just locks. You absolutely can. It's just that there are certain problems which are phrased more naturally and are easy to implement with semaphores. And one of those is producers and consumers. Now, there are many, many different synchronization problems. And if you take CS350, which I highly recommend that you do, I know it's not required anymore, you'll learn all about these other problems. So there's famous ones like the baker's algorithm, there's the barbershop, there's the dining philosophers, there's a whole bunch of silly named ones. But one of the most famous is the producers consumers. So essentially what you've got is some kind of bounded buffer, and you've got some threads which are producing items for the buffer and some threads which are going to consume items from the buffer. You can think of it this way. So let's suppose that you are a bake shop, and in your bake shop you have only so much room in your display cabinets for cupcakes. So when you wake up in the morning, you're going to need to start making cupcakes, but once the display cabinet is full, if you produce any more cupcakes, then they have nowhere to go and you end up eating them all, and then you go into some kind of diabetic shock. We don't want that to happen. And also you'd be wasting ingredients. And at the same time, for the consumer, what you don't want to happen is you don't want the consumers to come out to your bake shop and then find that the display case is empty because you have no items there ready for them. So we want some mechanism to synchronize the producers such that they never produce items if there's no space, and you never want consumers to come and get an item if there's none available. And what's interesting is we can actually use some semaphores to implement this. Now, this is normally where I would give you an opportunity to give it a try, but we're not going to do that today, obviously. So to solve this producer-consumer problem, we need at least 2 semaphores, because the thing that is a resource to the producer is different than what is a resource to the consumer. So to the producer, the resource is the available space in the baking cabinet, the number of empty spaces in the bounded buffer. And to the consumer, the resource is going to be the number of cupcakes on the shelf, or the number of items that are in the buffer. So since the resources are different, we're going to have 2 semaphores, one to represent the items in the buffer and one to represent the spaces in the buffer. Now, you'll note that when we start out, we have no items in the buffer and we have n free spaces. A lot of people ask me, why don't we just use a single semaphore and check its counter? Well, number one, semaphores counters should be hidden from you. And the reason for that is because in order for you to test the counter in a semaphore, you would need to use some kind of mutual exclusion to do so, which means you'd need another lock. And that seems very silly because the semaphore would have to know about that lock and your code would have to know about lock, and that just doesn't make sense. So the counter is hidden from you, and because the counter is hidden from you, we can't just check, hey semaphore, how many resources do you have? So we're going to have 1 semaphore for each kind of resource. So then using producers and consumers is actually really, really simple. All we're going to do is in the producer, since the producer wants to consume a space, we are going to P spaces to try to acquire it. Once a space is available, we will add our item to the buffer. And since we just added an item to the buffer, we've incremented the number of resources available, and so we V items. And then if you look at the consumer, when the consumer wants to take an item out of the buffer, which would remove something from the buffer to create a space, which means that we P items and then we V spaces. Now, that's going to make sure that the producers and consumers are synchronized in that sense. But this code still contains a race condition. And the race condition that this code contains is the fact that even though producers won't produce unless there is space in the buffer, and consumers won't consume unless there is an item in the buffer, what you actually end up with as a problem here is you could have a producer and a consumer trying to add and remove from the shared buffer at the same time. So in order to fix this, what we're going to need to do is we're going to need to add a lock or binary semaphore around the access to the buffer itself. All right. So then, I'm going to skip this slide. How do we actually implement a semaphore? Well, this is something that is actually given for you. It's already as part of OS 161, and it's kind of one of those things that was needed in order to implement the OS, especially from devices which are pretty heavy on the semaphore use. So the Semaphores implementation, I've grabbed the necessary bits for P and V from the sync.c. And what you'll see here, and I've removed some of the bits and I've just put the meat and potatoes here, so there's some funny assertions and stuff, which are all very important but not important to the discussion we're about to have. So what you'll notice here, if you think back to the lock implementation we did yesterday, number one, I told you should look at the Semaphores implementation of P and V. But here's proof of that. If you look at this, you've got acquiring the spin lock and then atomically testing the counter. If the counter is equal to 0, that means there's no items available. So we lock the wait channel, we release the spin lock, we go to sleep, and then when we wake back up again to make sure that there's still a resource available, we're going to reacquire and recheck our counter. Once we stop spinning in here, or blocking, once we stop blocking, we're going to decrement the counter to take the item and then release the spin lock. And then we have similar behavior in V, and I want to point out it's really important, of course, that you call wake 1. Because when the semaphore is getting a resource, that could change the conditions for the threads that are waiting on the semaphore, because now a resource is available. So always make sure that you wake 1. And the same is true in lock acquire. And I'll actually just I don't know how to get back to my previous page. There it is. You'll see here in our lock implementation that we, again, for release, we made sure that we woke 1 thread when we release the lock. If you don't do that, what's going to happen is that thread will stay asleep forever and nobody will be able to nobody will be able to wake it up. So make sure you don't forget this waking part. Really important. Now, I said yesterday that we were going to take a closer look at these 2 lines of code right here. Why do you have to lock the wait channel before you release the spin lock? So let's look at that. So let's suppose that we have an incorrect implementation of the semaphore where those 2 lines have been swapped. So you release the spin lock and then you lock the wait channel. So what's going to happen there, if we watch real close, is thread 1 is going to call P. And then when it checks the count, it notices that the count is 0, so there's no resources available. And then it releases the spin lock immediately after that count check. Then we get a context switch. Now, after the context switch, thread 2, which is the thread that's trying to release it, is going to execute V in its entirety. So it increments the counter, it calls wake 1, and then it releases the spin lock, and we get a context switch back to thread 1. Now, thread 1 is going to wake up and immediately execute the next instruction, which is wchan lock. Thread 1 is under the impression that the counter of the semaphore is 0, but because of this line here, that's simply not the case. Which means that thread 1 is going to fall asleep on a semaphore that technically has a resource available. So in order to prevent that from happening, you have to lock the wait channel before you release the spin lock. Because what that's going to do is it's going to prevent the releasing thread from actually performing the release until you have safely fallen asleep on that wait channel. So if we have a context switch after spin lock release in the correct implementation, then what's going to happen is even if, so let's say thread 2 calls V, it tries to acquire the spin lock, it gets it because you've released it, it increments the counter, but when it calls wake 1, and it's not really clear in this particular slide, but when it calls wake 1, it can't succeed. It ends up having to wait because the lock is owned on the wait channel, so we can't, in thread 2, actually access the wait channel. So we get a context switch back to thread 1, where thread 1 immediately falls asleep, releasing the wait channel lock. Context switch, of course, back to thread 2, who can now complete the wake operation, waking up a waiting thread, and then, of course, releasing the spin lock. And then the thread 1 would end up going from the blocked state back into the ready state. So that's kind of fun. All right. So that is why we have this. Now, if you are still struggling with why these have to be in this particular order, if you look on the Piazza thread for extra notes, you'll actually see I go into greater discussion with this for locks, but this and the same text actually applies to the semaphore implementation as well. So by all means, please do take a look at that. All right. So let's take a break for a moment and have a word from our sponsors.
Why buy just a video game from Atari or Intellivision? Invest in the wonder computer of the 1980s for under $300, the Commodore VIC-20. Unlike games, it has a real computer keyboard. With the Commodore VIC-20, the whole family can learn computing at home. Plays great games, too. Under $300, the wonder computer of the 1980s, the Commodore VIC-20.
Coming soon, Commodore brings you Gorf, the Wonder arcade game, and Omega Race in home versions. Commodore.
All right, I'm kidding. We don't actually have any sponsors. I couldn't resist. It was funny. All right. So that's the end of the discussion of semaphores. So the next synchronization primitive that I would like to talk about is actually the condition variable, which is the next part of assignment 1. So you've got two synchronization primitives that you can kind of consider a general use. You've got locks that block, and you've got semaphores, which can take the place of many different kinds of synchronization. But now we want to talk about condition variables. Now these ones are kind of weird to think about, but here's how they work. They work with a lock. And the idea behind a condition variable is, let's suppose that you're in a critical section protected by a lock. And in order to proceed in the critical section, you need the value of x to be 5, but x isn't 5. But the problem is you own the lock to protect variable x. So how do you wait safely for x to become 5 while you own the lock and nobody else can change it? So we need some safe way of releasing the lock and letting another thread modify x, and then once x has been modified, you go back as if nothing happened. And that's what a condition variable is going to let us do. Now there are 3 functions that are available with the condition variable, and they are wait, and that is we're going to force the thread that calls wait to block. And when it calls wait, it's actually going to be releasing and acquiring the lock safely. And we'll look at the implementation there. And so wait is to put the thread to sleep, to actually wait. Signal is to wake a thread up. And then broadcast is to wake all threads up that are waiting on the particular condition. Now, how does this actually work? So here's what's going to happen with the condition variable. So let's suppose that you are at a bar and you're sitting there at the bar and you have a pint of beer. I don't have beer, I have lemonade. But let's suppose it was beer. So you are, because your hand is on the cup, you have the lock on the cup and only you can use it. So you pick up your glass, you bring it to your mouth to take a drink, and you realize it's empty. Okay, I know my cup is not empty. Well, let's suppose it was empty. So you look at your cup and you're like, oh crap, my cup's empty. But you can't do anything about it because only the bartender can fill your mug back up again. But of course, you have the lock on the cup. And what are you supposed to release the lock and go about your business? You can't take a drink if you don't have the cup in your hand. So what the condition variable is going to let you do is you're going to fall asleep, and when you fall asleep, you're going to release the cup. At which point the bartender can grab the cup, fill it back up again, and then they are going to throw it down the bar at you. It's going to hit you on the side of the head. You wake up, and you simultaneously wake up, and you grab the cup, and oh look, the condition has changed. So you can take a drink. So that's what a condition variable is going to let us do. It's also apparently going to let me splash lemonade all over my glasses. All right. So how are we going to implement this condition variable? Well, first off, we should have a little discussion about the conditions. Now, it's very easy to believe that oh, that's not clean. So it's very easy to believe that the condition that we're waiting on is part of the condition variable, and that is simply not the case. The condition variable is simply a safe holding ground for threads waiting. So the condition is going to be managed by the developer, and it's going to be on the person using the condition variable to actually manage the condition itself and call wait and signal appropriately. Now, if we go back and we think of that producers and consumers problem, we could actually completely rephrase it, and we'll look at the code for this in a minute, to use a condition variable by simply realizing that there are two conditions. The producer's condition is that the number of items in the buffer is less than n, and the consumer's condition to operate would be the number of items in the buffer is greater than 0. So any problem that you can actually phrase for a semaphore, you can rephrase for a condition variable. And conveniently, you can also rephrase to use just locks. So how do we actually implement it? Well, let's start by just trying to implement this with a lock. So let's suppose you're trying to write some web app to help students who are on campus walk to their classes. Obviously, the slides were made when we had in-person classes. So in order for it to be safe to walk on your path, there cannot be any geese on the path. So I'm going to have a variable, a global, called the number of geese on your path. And right now it's 100. And if you've been on campus, if you live in the Waterloo area, there are hundreds of geese on campus right now. And then we have a geese mutex, and this is going to be our lock that we use to protect critical sections that are trying to access the number of geese. So in safe to walk, in order to check how many geese there are, we first acquire the geese mutex. And we're going to check then, is the number of geese greater than 0? Because if it is, we need to wait somehow. So how are we going to wait while safely releasing this lock? And actually, you can use a while loop and do what I did to show you how to do the semaphores with just a lock. It's the same idea. So what we're going to do, and again, this is incomplete pseudocode. I know there is a release that should be down here at the bottom. It's pseudocode, right? So we acquire the lock for geese. And then while the number of geese is greater than 0, what we're going to do is release the lock. And you can put a yield here to encourage a context switch, and then we reacquire the lock. So we are going to actively wait, that is busy wait, until the number of geese is finally equal to 0. And once it's equal to 0, we would continue on with the body of the safe to walk function. Okay. I don't like this though. I don't like how we have this code and this code out here, because this is the kind of thing where you're assuming that the developer knows what they're doing and they're going to do it properly. And it's really, really messy. So this is where we can actually use a condition variable to help us out. So if we take the same code as before, we still need the geese mutex because that's what's giving us the mutual exclusion on number of geese. But now we're going to add a CV, and I need to name my CVs according to what the condition is they're waiting on. So I've called this CV 0 geese. So I am going to acquire my lock on the geese variable, and then I'm going to say while the number of geese is greater than 0, instead of acquiring and releasing the lock, I'm going to call CV wait. And now you might be wondering, well, is this still a busy wait? Yes and no. So here's the thing. CV wait is going to use a wait channel, as we will see. So if you call CV wait, we are going to release the lock, we're going to fall asleep, and we stay asleep until someone signals us that the condition has changed. And then we'll move from blocked to ready. Why then do we need to use a while loop around this condition here? The reason for that is because most uses of condition variables, it is entirely possible that once you have been signaled, you don't run immediately. You go from blocked to ready, and that means there could be some time before you actually run and make note of the fact that the condition has changed, which means another thread could run in front of you and change the condition back. So if that is how your code is running, you're going to need to use the condition variable with a while loop. Now, does that mean you're going to use while loops with condition variables all the time? Not necessarily. You can use, in some cases, a condition variable with something that I call an explicit handoff. So you can have the signaling thread change the state for the next thread that will be running, which will prevent or block any of the other threads that may sneak in from changing the state back. And if you can do that explicit handoff, and we'll do an example later, the while loop isn't needed. But most times we do need the while loop here. All right. So then let's, instead of talking about the implementation right now, I'm actually going to come back to this. What I would like to do is show you how producers and consumers would work with condition variables, and then we'll talk about the implementation of condition variables. So to start off with, we've already alluded to the fact that the conditions are, again, specific to the type of thread. So our producer thread's condition is going to be that the count is less than n, and our consumer's condition is going to be that the count has to be greater than 0. So we're going to have one lock to protect the count of the number of items in the buffer, and then we're going to have a CV for the buffer being not full, and a CV for the buffer being not empty. So then in produce, we need to check, can we add something to the buffer? So I need to check my count. So I acquire the lock on the mutex. And then I am going to say, well, is the count equal to n? Because while the count is n, it means the buffer is full. I'm going to call CV wait on not full, because I'm waiting for the buffer to be not full. Once the buffer is not full, and I've woken up and it's still not full, then I can safely add the item to the buffer. And then I increment the count because I have added an item to the buffer. And since I added an item to a buffer, I changed the condition for the consumer thread. So what I do now is I'm going to signal not empty, so that any thread that is waiting for items to be in the buffer can wake up and move on. And then I'm finally done, so I release the lock. And the consumer for this looks pretty much the same, except we're going to have a different condition, and we're going to signal and wait on different CVs. So in the consumer, we are waiting for the count to be not 0. And so we are waiting for not empty. And once we have found that the buffer has an item in it, we take the item off, we decrement the counter, which changes the condition for the producer. And so we're going to signal not full because the buffer is no longer full. We release the mutants. So there you go. There's a few examples of how we actually use these condition variables. And now the question becomes, how exactly are we going to implement them? So let's switch over here to OneNote. And let's make a new page. And let's give out some nice lines so that you can actually see what I'm doing. And let's actually draw out our CV wait. So let's make some notes here first. So I know that my CV is a safe waiting space. Okay. So I probably am going to need something in my condition variable to wait on. So my CV needs a wait channel. Now, a lot of people get confused here and they think, well, why can't I just use the lock's wait channel? The lock's wait channel is for threads waiting for the lock. If you are waiting for a condition, you are not waiting for the lock. So the CV contains its own wait channel, and that wait channel contains only threads waiting for that specific condition. Now, when you call wait, we need to simultaneously release and sleep. And also, we need to make sure that when we enter wait's function, we own the lock. We need to make sure that when we leave wait, we still own the lock, so that the thread that called CV wait knows that outside of CV wait, it is protected. So when we call wait, we need to be able to release and sleep simultaneously. And when we return from wait, we still need to own the lock. So how can we implement this? Now I'm going to give you a very rough pseudocode implementation of CV wait. I'm going to leave out some steps that I'm going to let you fill in, and I'm certainly not implementing signal and release. For the record, these took me about 2 minutes to implement, and I think like release or signal and broadcast are like 2 lines each. They're quite easy to implement. So let's look at CV wait. So CV wait has 2 arguments. One is a CV and one is a lock. So details, details, details. I'll let you fill that in. What we're going to need to do is simultaneously release our lock and fall asleep. We know how to do this because we've already done it in a lock and we've already done it in a semaphore. But instead of using a spin lock to do it this time, why don't we just use this lock right here that's passed in? So what we're going to do is lock the wait channel. I'm not telling you whose wait channel. I'll let you fill that in yourself. And then once the wait channel is locked, I release. Okay. So we've entered the wait channel, or we've entered CV wait. We owned the lock while we entered CV wait. We've locked the wait channel, we've released the lock, and then we call wchan sleep, of course. Not too bad. So At this point right here, the caller is asleep. And when signal is called, the thread wakes up right here. Now remember, there could be some time between we call signal and this thread actually running. But when it does actually run, it's going to wake up inside of CV wait. Now we need to make sure that when we leave CV wait, we still own the lock that was passed in. So what we're going to do before we leave CV wait is acquire that lock again. So that lock there is also that lock there. Not bad, right? So there is some details missing that you need to fill in and some pseudocode here. It's not too bad. So that is how you implement CV wait in a nutshell. And again, really, signal is fairly straightforward. Signal is supposed to wake one thread, and broadcast is supposed to wake all of the threads. And I'll let you decide how you want to implement that. If you find yourself trying to add a spin lock or a lock to the wait to the CV itself, you've gone down a garden path, and don't be afraid to ask some questions on Piazza. CVs, by the way, don't keep track of owners, so you don't need anything like that. All right, so let's suppose that you've gotten this part of the assignment done, and you're wondering, how am I going to test condition variables? So let's go over here to a lovely terminal. And what I want to do is I'm going to show you the code for CV tests. Let me just look up here my line numbers, which I always forget. There they are. So we are in the directory kern test, and we're going to open synctest.c again. And we're going to go down to line 261. Now remember that there are 3 shared variables in here. There's test val 1, test val 2, and test val 3. Those are global shared variables for all of the threads. So on line 261, this is CV test thread. Now it's not going to make too much sense to you in here because it's got all this time code. But this is the test, and I'll show you what it does in a minute. And the idea is if the test fails, that is, your CVs don't work, you're either going to get nonsense output, or more often than not, you also get this, that's too fast, you must be busy looping. So you should see a perfect output here. So what is the output of this CV test thread? Well, this is the SY3 test. So let's run SY3. So SY3, you see here, and you'll note I'm running this from the command line because it's going to make testing easier. So we run SY3, and this is what you should see. You should see 32 threads sound off in reverse 5 times. So if you see nonsense, if you see that bit about the threads going too fast, your CVs don't work or your locks don't work. So this is an interesting thing to note about testing your condition variables. Your condition variables require that your locks work properly. So don't even try to attempt to implement the condition variables unless you are 100% convinced that your locks work. And remember, the best way to test whether your locks work is whether or not is to do a statistical evaluation. So we have a question on Piazza about, out of curiosity, what happens when kassert false is called? Does it print an error or just quit? I don't know because I've never typed that before. But if only you had the operating system sitting in front of you and the ability to call that code right now. I mean, we could do it, but it'd take me a few minutes to get my compiler back up and running. All right. So let's see what happens if you run SY3 without CVs implemented or locks. So I'm going to use my assignment 0 kernel. Oh, there you go. Look at that. Garbage. So the only thing you should see if your CVs work is the 32 threads sounding off in reverse 5 times. So after you've fully tested your locks, and remember that you need to test your locks on 1 CPU and then 4 CPUs, once you are 100% convinced that your locks work, and you should do this by running your tests at least 100 times per CPU configuration, only then do you implement your CVs. Once you have your CVs implemented, make sure you run SY3 again 100 times on a single CPU and then multiple CPUs. Now, what tests are we going to do for CVs for you? We are going to run SY3 because that's what we have available to us. So you have the source code to it. I've already showed you that, and you have the test and you can run it yourself. A couple things I want to make note about the grading for locks and condition variables. It is very rare in this course that we actually open up your code and look at it, but for locks and CVs we are. So we're going to verify that with locks you're using lock do I hold instead of just checking ownership directly, and the same is true for condition variables. We're going to be checking to make sure you use lock do I hold instead of just asking directly. Another thing is we're also going to check to make sure that your lock isn't just a wrapper for a spin lock or a semaphore. And we're going to check with the condition variables that you have all of the right assertions. And we may also check details just about the implementation. We are not grading your style. Now, even though we are not grading that style, understand that if your style is really bad and you've named all of your variables A, and A, you're going to make the TAs very, very unhappy. And then if you ask for help on Piazza and that's what your code looks like, I'm probably not going to help you either, because your problem is that you named all your variables variations of the letter A. And if you're wondering why I use that particular example there, because surely nobody has named their variables A, and A. Oh, I wish that was the case. I have some MATLAB code where they literally named their variables A, and it's not helpful. All right. So on that note, you've seen how to test locks, you've seen how to test your condition variables, you've seen how to implement condition variables, and you have also seen how to implement locks in the last 2 lectures. Which means you now have, as of this moment, enough information to implement assignment 1 in its entirety. And what I'd like to do in the last few minutes of this lecture is just give you a few pointers for assignment 1's traffic simulation problem, which is the last part of the assignment. So first off, you have to use for the traffic simulation, what you have is a 4-way intersection, and you've got a traffic light, and right now it only lets 1 car in at a time. So it's the world's worst intersection. So what you need to do is increase the throughput of the intersection while making sure there's no accidents. So a couple pieces of advice I'm going to give you is that I highly recommend you use locks and condition variables and not semaphores. It's not to say you can't get it working with semaphores. It's just to say I don't think I've ever seen a student get it working within the time constraints for semaphores. The other thing I want to say is that you can't use weight channels or spin locks. You have to just use locks, condition variables, and semaphores. And if you have 12 or 16 condition variables, you're going to have a really bad time. The correct number you need is just 4. Just 4. I'm not telling you what they're for, but 4 is a good number. The other little hint that I want to give you right now, and I will give you more hints eventually, but the hint I want to give you now is if you look at the rules of the traffic simulation, there are 3 rules at the very bottom, and it's very tempting to believe that you must permit all of those things. And I want to say you don't have to permit them. Those are just the rules telling you when accidents happen. So if you want to further simplify traffic to make your life easier, I recommend you do so. I suppose for me it was fairly easy to implement this because I actually don't have a driver's license. I've never read the driver's handbook. I don't know the rules of the road. So I I don't have reality impacting how I implemented the traffic simulation problem. So that's actually a good hint for you. Drop all of your notions of real traffic and just make it work. All right. The other thing that I wanted to mention, and I mentioned this far enough in advance, is if you're using condition variables and the condition variable is in a loop, you're going to have a really bad time. So we'll post more hints, and I will post some test values to Piazza as well, so that you have an idea of what are the numbers that we're going to run through. So I want to leave you then, before we go, with a sample problem. This is the sample problem uploaded to Piazza known as Sem2CV. And what you have here, we're not going to take this up today, is we have a little bit of code, function 1 and function 2. And right now the synchronization is entirely provided by these 3 semaphores. And what we would like you to do in this particular problem is replace the semaphores with locks and condition variables. So get rid of the semaphores. But in order to do this, we want you to maintain the functionality that we have here. So don't change how threads are going to go through these 2 functions. So with that, what are we going to cover in our next episode? So in the next episode, which of course will be Tuesday of next week, we are going to take up the solutions to Sem2CV. We are also going to give you a few more hints about assignment 1's traffic problem. And then we're going to move on to talking about how race conditions can arise from your compiler and the CPU. And we'll of course talk about deadlock as well. So we will see you next week on Tuesday, and I hope that you have a wonderful weekend.
Let the Radio Shack TRS-80 put the world of color computing into your home. Instant loading program packs turn any color TV into an exciting game arcade. And there's more. The color computer is an educational aid, a home management tool, an up-to-the-minute electronic information service. The programmable, expandable TRS-80 color computer from $399 only at Radio Shack, the biggest name in little computers.